Hi guys, it's going to be a video lecture about dynamics. Alright, forces and their properties. Force is simply pull or push, and they all have source and certain direction. So we have a lot of different types of forces. So the first one, or not in order but in the name order, applied force, drag force, friction force, gravitational force, normal force, spring force, or frictional force. So these are basically the names, and they all have certain directions. So to be able to, for us to tell what forces we have in the system, actually this table is going to be, it seems simple, but this is basically in the core of dynamics. So knowing what forces we have in the system and figuring out their directions and knowing the equations that we have for those certain forces. So applied force is going to be in the direction of whoever is applying it. And what is the reason? When do we say that there's an applied force? We need to have someone outside force, and most of the time it's by person. Drag force, it's basically in the direction of opposite of the movement. Object is going down, drag force is going up. And what is the reason? What is it? When do we have air resistance, or when do we have drag force? If we are moving in a fluid, or if there's an air in the system. And there's an extra equation for that, but you don't really need to know that at this point. Drag force is going to have negative BV equation. Friction force is also opposing force, so it's going to go against the movement. And when can we say that there's a friction? First, it might be like stated, or if they say rough surface, then we know that there is a friction in the system. And friction force is going to have an extra equation, which is normal times mu, which is coefficient of friction. And gravitational force, it's straight down. And a reason for gravitational force is basically a planet or some like heavy mass technically. And a way for us to calculate the gravitational force is mg. And normal force, it's perpendicular to the surface and it's away from the surface. And when do we have normal force? We basically need to have a contact with a surface. So, and what is the equation? There's no certain equation, but it's going to be the sum of all forces that is acting towards the object. And spring force is going to be along the string, and spring, and you are going to need a spring to have a spring force because you need something elastic. And a way for us to find the force created by the spring is K times X. X is the distance that you stretch or compress, and K is going to be the spring force or spring constant or force constant. And tension is again along the wire. And when do you say that there's a tension? You basically need to have a wire, string, or a rope that is light enough and not elastic. And if you would like to see more details about those, you can actually click there and then you will be seeing more details about them. Alright, free body diagram. This is after you know which forces you have and what the directions are, you are basically able to sketch the free body diagram. This is like the actual key thing for dynamics questions. Once you are able to have this free body diagram correctly, then the rest is just going to be applying one equation. And what is a free body diagram? It's basically a pictorial representation of all forces and acting on the object. Alright, because sometimes, and actually not sometimes, most of the times we're going to have objects applying forces around themselves as well, but in the free body diagram we only care about the forces acting on the object that we have. And we are showing them with the vectors and the labels away from the object, and object is represented with a dot in that case. So in this case, since it says, so sometimes they're not going to tell you that it's a rough surface, but you need to be able to actually see the given information and then figure out some of the forces accordingly. So in this case we have gravity. Since it's always straight down, we have straight down gravity, since we have a surface, we have a normal force going away from the surface. And normally you expect this guy to fall or like slide, but it's not sliding. It says its initial, like its velocity is 0. So that means there is something that is preventing this guy to move down. So intention of the movement is down, but the force of friction is basically keeping this guy away from movement. So it's going to basically go against the movement, which is up. Alright, first law of motion, it's also known as the law of inertia. The common way that we know it is object at rest wants to stay at rest, object in motion wants to stay in motion if there's an unbalanced force acting upon it. But more scientific definition is basically when net force acting on the object is 0, then you expect one thing or two things. There is no change in velocity. So change in velocity is 0 means if you are at rest, you are going to stay at rest because there's no change in velocity. And if you are going at a constant speed, then you are going to continue to that speed because that's what inertia tells us. So that's where it's coming from. The idea of inertia is basically having a net force of 0. And inertia itself has a different meaning. Inertia means tendency of an object to resist the changes on its state of motion. So that's why if the state is at rest, then it will resist to stay at rest. If it's in motion, it will start or will resist to stay in motion. So if you want to change it, then what do you need to do? You have to apply a net force. Alright, if there's no net force acting on the object, then there is no movement. Objects will resist moving or changing their state of motion. And what is it about? It is about mass. So more mass means more inertia, or heavier objects will require more force to accelerate them. Alright, second law is basically this simple equation, F equals ma, or total force equals mass times acceleration, and it basically means more mass or more force will accelerate the object more, but as the mass increases, the acceleration will decrease. Alright, and we are going to be using this equation in both x and y axes because you're going to have basically 2D motions most of the time, or forces, since they are vectors, you can have them in two different dimensions. So that means you're going to need fx equals max and fy equals may. And third law is action-reaction principle in simple terms. So, and what does it state? Every action, there's an equal and opposite reaction, and they act on different objects. Alright, this is actually the key thing about action-reaction principle, because if action-reaction, since they are in the opposite direction and equal to one another, they should basically cancel each other out and we shouldn't have any force. But since they are acting on different objects, then both of the objects are basically going to have the effect of the force. So that's why third law, this key point is important. And all forces, this is another very important point. All forces come in pairs. There's no force that is just alone. Alright, so any force that you draw in a free body diagram, they must have the opposite or reaction force along with it, and they are going to be applied in the opposite objects basically. And those pair of forces act on objects that are in interaction. So for example, when we are dropping something, it falls down, right? What pulls it down? Earth. That means this guy is also pulling this guy up. So all forces comes in pairs. Alright, single object dynamics properties. So once we have one single object in my system, or in the case, then we are going to start with drawing with we always start with free body diagrams, and we draw x and y coordinates with dashed lines, determine positive and negative directions. If there's a vector with an angle, find its components, add or subtract depending on the directions all forces on both axes separately, and then solve net force equals ma for both of the axes. So at this part, I'm going to be basically shoving 1,000 different cases, and then I am not going to I will try not to talk too much. I will just shove them separately, and then I expect you guys to basically get the idea of how to draw a free body diagram. These are different cases, and there's no solution. I just basically write down or show you how to move, how to start, and how to actually construct the equation. And we always start a free body diagram. Since I have 3 different things acting on it, it is with the strength, tension, or sometimes it can be shown as Fa, gravity pulling down. There's a surface, there's a normal force, there's no friction. So since I have a force with an vector, what do I need to do? I need to find its x and y component. Depending on the angle, I use sine and cosine and find tx and ty in terms of theta. And after you basically find the components of this guy, you erase this and then you replace it with the tx and ty, and then you have your new free body diagram. And then on the x-axis, you only have tx, so tx equals ma, and tx is basically ft cosine theta, max. And on the y-axis, you have basically 2 forces going up, 1 force going down, but this object is basically not moving up and down, so that means your acceleration on the y-axis is 0. So that means forces going up is equal to forces going down. So Fn plus Ty, which is Ft times sine theta, is equal to mg. Second case, you basically have objects suspended in the air and you have 2 strings attached to it. So T1, T2, well, one of them will be T1, doesn't matter. So, and one of them is not on the axes. So what are you going to do? Find the components of it. And then you are basically going to replace this with the forces, with the components of it. Write everything down that you have on the x. T2x going to the right, T1 going left. So basically that's how you put it. And since the object is at rest, there's no movement, there's no acceleration. And on the y-axis, same idea, going up, going down, no motion, no acceleration. Forces going up equals forces going down. And since you have sine theta in both, you can combine those 2 equations. And third case, you're going to have friction this time. The only thing that is going to change is you're going to add a friction in the system. And since you are tending to move the object in the right, your friction is going to be to the left. And even if you're applying the force from top, it's going to go away from the object. So you need to be careful with that free body diagram. Again, you have 1 force with an angle, so find a component and replace that vector with an angle with the components. Write down everything that you have in the x-axis. Write down everything that you have on the y-axis. But in this case, we are going to require a friction force. And friction force is going to require what? Remember, it's also going to have its own equation, normal force times mu. And for us to be able to find the normal force, we basically need to visit the y-axis because forces, the normal force is on the y-axis. And for us to be able to find it, and there is no movement on the y-axis again, so that means forces up equals forces down because acceleration is 0. Then what am I going to do? I am going to replace this Fn that I found from the y-axis into the equation and then solve the rest. These are again a way for us to construct the equations. This is not a solution to the questions most of the time, but these are basically the steps that we follow. Once you figure out how to set it up, then it will be easy for like any type of questions that you have. All right, for elevators, the first one was single object, but elevator is a different case. I mean, idea of free body diagram is not changing, but for elevators, we are basically moving in an elevator, we go up and down. So for those cases, in a free body diagram, we always have two forces, normal force and gravity. And normal force is always going up, mg is always going down, but the only thing that is changing in those cases is the acceleration. So depending on the sign and magnitude of n, depending on the sign and the magnitude of acceleration, Fn will be different. If there's no acceleration, your weight will be the same. If A is negative, you weigh less. If A is positive, you weigh more. If, when you're in the elevator, the wire is cut, then you're going to basically weigh nothing. So it's going to be weightlessness. And Fn is what person weighs on a scale. Alright, so that's basically what we have. Alright, so objects, basically elevator going at constant speed, no velocity, no acceleration. My free body diagram, Fn goes up, Fg goes down, but since there is no acceleration, Fg and mg are the same, so you weigh the same. So on the scale, you're going to get what you are actually weigh on the ground. If you're going down, then what's going to happen? Your gravitational force is going to be greater than your normal force. Why is that so? Because total force on the y is Fn minus Fg. But since you're accelerating down, the sign for the acceleration will be negative, and your Fn in that case is going to be mg minus a. Alright, and basically you weigh less than what you actually are. If you're going up, then what's going to happen? This time you're going to weigh more. And how is this happening? Again, Fn goes up, mg goes down, but this time your acceleration is positive. So your Fn is m times g plus a, so you weigh more than what you are. And actually for those cases, you can just think about it. So when you're in the elevator, once you press up, which means you're accelerating up, you basically feel like you're pushed down. So you basically feel heavier. Or once you're basically going down, you basically feel like lighter. So you can just think about that concept as well. But mathematically, that's how you solve it. If it's cut, then your acceleration will become g. So in that case, your normal force, actually this is wrong. Well, by free body diagram, that's how you draw it. But technically, you're not going to have this guy. Why is that so? Because Fn minus mg is equal to minus mg. So your normal force is basically 0. Alright, so if you have more than one object in your case, then that's going to be a system. And for a system, we basically, instead of drawing going with single objects, we basically try to figure out what's happening to the system. So we are trying to figure out a force, net force that is moving the system. And we take the mass as system, which is total mass of everything, and acceleration of the system. And one good thing about this system equation, since everything is connected, everything is going to have the same acceleration. So once I know the system acceleration, then I will know acceleration of the individual objects. So that's why we basically use this equation. Alright, so there are different cases for systems. So the first one is pulley. One object is on the table, the other is basically suspended in the air. So what is my system? Or what is the force? Only force that is moving the system is basically force acting on this guy. And tensions and action-reaction pairs are not going to be part of the system force because this guy is pulling it this way and this guy is pulling it this way. So internally they cancel each other out. So the net thing net force that is getting the system move is gravitational force acting on the second object. So mg2 or m2g is the net force on the system, and this force is basically moving m1 and m2 together. So mass of this system is m1 times m1 plus m2 times acceleration of the system. So, and if you would like to know the tension, or later on maybe friction, then what do we need to do? We are going to need to find individual objects in this case, and you draw your individual free body diagrams. So first object is going to have tension, right? Normal force up, Fg goes down. But since there's no motion in the up and down direction, those two forces are going to be equal. But since second object is going down, Fg is supposed to be greater than Ft. And for the first object, we have motion in the x and y axes. So on the y-axis, there is no net force. So forces going up equals forces going down. And on the x-axis, you only have tension force, and it's basically m1 times acceleration of the system. Actually, there's a mistake over here. So this is going to be 0 because there's no movement on the y-axis in terms of like motion on the y-axis. So that's going to be 0. So your Ft is I don't know. I think I made a mistake over here, but since we're talking about M2, never mind, no. So we are basically having a motion about the motion in the y-axis for M2. So there are two forces. Ft goes up, M2g goes down. Here, one thing that you need to be careful, since system is moving down, your acceleration for the second object will be negative value. If there's a friction, then what's going to happen? In the system, there will be two force effective. This guy will try to move it down, but this friction acting on M1 is going to resist the motion. So in this case, M2G minus M1G, which is the normal force, times mu, which will be the friction acting on the first object. And this is going to be equal to mass times acceleration, and mass is the total mass, which is m1 plus m2. And free body diagram for both of the objects. Then on the y-axis of m1, you are going to have no movement on the y-axis, so that means acceleration is 0. So Fn1 is equal to basically how much it weighs. So that's why your Fn right here is multiplied with mu to find the friction force. And you can directly find your friction force by multiplying your normal force or your weight of the first object with mu. And x-axis for the first object, and y-axis for the second object. And you can use both of the systems or both of the free body diagrams to find the tension. You just need to be careful that they both should be the same, because tension along the same string is going to be the same throughout. And Atwood machines, it's a little bit different version of play questions. This time both of the objects are basically moving on the y-axis, so they're a little bit simpler because there's no x-axis, there's no friction. So in this system, we basically have two weights, and one of them two trying to move the system, but they're going against each other. One is trying to pull it up, the other is trying to pull it down. They always goes against each other, so you need to subtract them. So which one do we subtract from which one? Whichever is greater, then you basically subtract it in that direction. Alright, so in here, my M2 is a larger mass, so I basically put it on as positive. And M2 will be moving down, and M1 will be going up, so this is going to have a positive acceleration, this is going to have a negative acceleration, but the same acceleration. Free body diagrams, and then you basically evaluate what you have, the total forces on the x and y, and that's going to help you to find the tension. And you can also have two strings attached together and then moving two objects moving together. So in this case, in the system, there's only one person moving the system, and that's person. So you only have F applied. To be able to find a tension in between, you basically have this tension in both cases. On both y-axes, there is no motion, so you don't need to worry about it, and there's no friction, so you're not going to need normal force anyways. So you don't need to worry about what you have on the y-axis. You just worry about what's happening on the x-axis. And you always go with the same scenario. Write down Fx equals ma. Look at the force on the x-axis, look at the force on the y-axis. So for the second object, Fa goes up, right, this is positive. Ft goes left, this is negative. For the first object, there's only Ft that is going right. So that's all you have to do. Just write down all the forces and then use them in the dynamics equation. If there's a friction, it gets a little bit complex with that system, but that's because you have two different frictions. So my system is going to basically this guy trying to move, this resistant resists, and this guy is also resisting. So you're going to have basically three different forces this time. So Fn times mu, Fn2 times mu, and so to be able to find your normal force, you're going to need your y component, like y-axis. But since there's no motion in the y-axis, you basically have normal forces as your gravitational forces. So your F1 is basically m1g, F normal for the second mass is basically m2g, and your friction forces basically multiply with the mu. And what's happening on the x, for m1 you only have friction and tension, but for m2 you have applied friction and tension. And tension is trying to pull it in the other direction, and friction is also trying to resist the motion. So once you basically plug in everything with their equations, then you're going to basically have those setups. Alright, another case. This time there's no string in between, but those two objects are basically in contact. So in that case, again, there's only one force that is getting the system move, and that's the applied force. But action-reaction pairs in that case is going to be important because most of the time that's missed. So Fa, this guy is pushing the first object to the right, but when this guy is pushing it, the second guy is pushed. And this is basically creating a friction, contact in between. If there's a contact, there's technically a action-reaction force. So M1 pushes M2, but M2 pushes M1 back. So basically F2, second object on the first object. And it's basically going to the left. But another mistake that most students do, on object 2 there's only one force, and that's basically M1 acting M2, because this person is not touching M2, so there's no force created by the person on M2, so it's only F1 on 2. And the rest, write down basically Fx and write all the forces going right as positive and for all forces going left as negative. And on the y-axis, there's no acceleration, so upward force equals downward force. So Fn's are basically equal to their weights. If there's friction, again, same scenario, but this time you're going to have resisting forces. Friction of the first, friction of the second is going to resist to the applied force. And you're going to need your friction forces, and you're going to need normal force for those, but since there's no motion on the x and y, your normal forces will be basically equal to your weights. And basically once you put everything together, all forces going right and left as positive and negative, then you will be able to basically get those final equations. I don't remember if you guys had those type of questions, but this is a little bit different than the rest. So in the bottom you don't have friction, but there is a friction in between two materials. So the total force for the system is again the applied force. Nothing else is acting on the system. But the free body diagrams are going to be a little bit different this time. So the first object free body diagram, you basically FG, which is gravity acting on this guy, applied force, which is this guy, and friction force. All right, this friction force is coming from the top object. All right, it's not the friction in the bottom, it's the friction created by the top object. And I'm going to revisit this guy in a bit and figure out why it's going left. And what else do we have? M1 is also pushed by M2, so there's F2 on F1. And friction force is basically F1 on F2, and we need to actually revisit this part as the second object. So once we look at the second object, so we basically have gravity acting down, and then we have normal force going up. But this normal force is actually the part of action-reaction pairs that you have in between M1 and M2. Yes, F1 on 2 is a normal force, but since I called it F2 on 1, then I just called it F1 on 2. So this is a normal force of M1. So because this is considered as a surface. So what is the direction of, so this F is not acting on it, but we say there's a friction acting on it, and we say that it's going to the right. So how is it possible this M2, if you look at the system, since there's a friction, this guy is actually moving to the right. So how is this guy creating the friction in the direction of the motion? So in this case, we are going to have a little bit inertia in here. So if we didn't have friction in this part, what would we expect? The force is acting on M1, so there's no force acting on M2, right? So if there's no friction. So what does that mean? This object would actually stay at this location, and that would move to the right, and then that would just fall. But since we have friction in the system, what is happening? This guy is moving to the right. So what does that mean? This guy normally would not move, right? Normally that would stay at the same location, but system is trying to get this guy move basically like this is gonna stay at this location. But what is happening? You are basically friction. So since that seems like it's staying over here, it's basically with reference to M1, M2 is moving to the left, right? Because this is moving to the right. So if you take the reference as M1, M2 is basically moving backward, or it tends to move backward, but it's not able to do so. Why is that so? Because there's a friction, and basically friction is taking it forward. And like we said, all action-reaction forces comes in pairs, or all forces comes in pairs. Since friction on the top is going to the right, then the friction on the bottom must go to the left. And this F1 on 2 and F2 on 1, those are two pairs, and those friction forces are pair forces as well. So considering that your friction force is the same for both, and it will depend on the normal force. And since it's easier to find the normal force from here, it's going to be basically F1 on 2 times mu, which is M2G. Looking at this free body diagram, there's only one force going down and one force going up, and that means my F1 on 2, which is F2 on 1, are the same, and it's equal to gravitational force of the second mass. And that's equal to basically mu times this gravitational force is equal to the friction, and this friction and this friction, they are action-reaction pairs, and they are also equal to one another. And after you basically write everything down and figure out what you have going up and down, you basically plug them in here. Force goes up as positive, force goes down as negative, and solve it for the case. And inclined planes are basically when you have a surface with an angle. Exact same thing, except this time your x and y components will be tilted. So normally we basically have our x and y as like this, but for inclines we basically choose the surface as your x and the line that is perpendicular to that as your y-axis, and nothing else is actually changing after that. It's just tilted xy coordinate system. Fg is still straight down. Friction is, if there's a friction, well, I said no friction, but I have it over here, so you just exclude this. So yeah, I solved it with no friction, but I just added the friction. So in that case, your F normal will be on the y-axis, but your Fg, normally it's always on the y-axis, but this time, since the x and y coordinates is tilted, then your Fg is going to be the vector with an angle, so we need to find the x and y components of this force. Then Fgx will be mg sine theta, and Fgy will be mg cosine theta. And then you basically follow the same procedure for x and y. F equals ma. Forces goes up positive, forces goes down as negative. And once you have friction this time, you are going to have this friction added. Nothing else is changing. Friction force is also on the x-axis, so you don't need to find the components of this guy. So only thing that requires a component is the gravitational force, same idea. And the y-axis, you basically have all forces written down, and on the x-axis you have all forces written down, and you basically solve Fn to be able to find the friction force, and then plug it in the x-axis. Alright, that is it. I know it's too much, and these are basically all, not all, but most of the possible cases that we can have. So the applications will be on basically the question solution part. Alright, see you in the next videos, guys.